Hello everyone, welcome to Gate Pass. In this video I am going to take the remaining 3 problems that appeared in Gate 2013 and which were related to thermodynamics. So let's start. The first problem which I have taken was question number 35. It asks you to calculate the heat transfer or heat that need to be supplied Q in kilojoules to raise the temperature of 1 mole of a solid from 100 degrees centigrade to 1000 degrees centigrade. They have given you the value of Cp as a function of temperature. The units are joule per mole per Kelvin, and they have said that with this particular relation you have to use temperature in Kelvin. Further, they have told you that there is no phase change which is taking place. So it's a very straightforward problem. For a solid, I can assume that the pressure is not changing much, and since there is no phase transition, then directly the heat which is required, that will be equal to integral of Cp dt. Since they have said temperature of 1 mole of solid, so I can write NCp dt, but N is only 1 mole, right? So I am right now forgetting about it. Fine. Now it's very straightforward. Just plug in, integrate, and then find the answer. So what it is 20 plus 0.005 T dt. The only thing which you have to take care over here is that when you are putting the limits of temperature, don't forget to convert them into Kelvin, because here you have been asked to use the temperature in Kelvin scale, So 100 will become what? 373 Kelvin, and 1000 will become 1273 Kelvin. So these were the limits these are the limits which you have to apply. So 373 and 1273. Now do the integration. It will be 20T plus 0.005 T square upon 2. Apply the limits. Solve it. I will solve it for you over here. So Q, that is equal to 18,000 plus, so if I do this, how much it will be? 1273 minus 373 multiplied with 20. So this will be 900. 900 into 20, that will be 18,000. So the first term is 18,000. Now second term you have to take the square. Do that, and the value you should get is 3703.5. Add it, and you get the final answer. I am getting it as 21703.5 joules. And if I have been asked to calculate in kilojoules, so that will be 21.703 kilojoules. So this is your answer. So it was a very straightforward problem. The only place where you can do a mistake is while applying the limits. If you put 100 and 1000, then this question will be wrong. Other than that, there was no trick in this problem. The next question which I am going to take is question number 8. It has asked you to find out which one is the unit of isothermal compressibility. So quickly we will see from where does you get the definition of your isothermal compressibility. We will write the relation, and then from that we will get the units of isothermal compressibility. So you all know we can write equation of state as some function of PVT. So I can write my equation of state as some function of PVT. Or I can also write it explicitly in V, and then that which is the molar volume, and I can write that V which is a function of P and T. I can write a total derivative of V now as dV is equal to del V by del T at constant P into dt plus del V by del P at constant T into dP. I can write it like this. Now these partial derivatives, they have some physical significance, and for liquids they have been tabulated. Now how they have been tabulated? They have been tabulated as the values of beta and kappa. So beta is known as volume expansivity, okay, and it is defined as 1 upon V del V by del T at constant P. Okay, so this is your volume expansivity. Similarly, minus 1 upon V del V by del P at constant T. This has been defined as isothermal compressibility because temperature is constant. Okay, so this is your isothermal compressibility. Both these values you can find in books. They have been tabulated for various liquids. Okay, so in this question they have asked you what are the units of isothermal compressibility. So what you see is volume, it will get cancelled. Only the pressure is remaining in the denominator, so it will have units of 1 upon Pascal or per Pascal. Okay, so this is the right answer. Now you can also find out what are the units of beta, that is the volume expansivity. It will be 1 upon Kelvin, or you can say per Kelvin. Okay, so it was a very straightforward problem. Now let's move on to the last problem in this video. So the last problem which I am going to take is question number 30. It talks about a process which is occurring in a closed system F. Okay, so let me draw a closed system F. So a process is occurring in this closed system and the heat is transferred from F to the surrounding. Okay, let's say this is my surrounding, this is E, and heat is being transferred Q, that is equal to 600 joules. Okay, so this is 600 joules. Fine. Temperature of the system, it ranges from 380 to 400 Kelvin. Now they have asked you what are the entropy changes in the system and the surrounding. So you have to tell which one of them is right. Okay, so it's a very interesting problem because they have not told you that this is a reversible process. Because if it was reversible process, you could have applied your Clausius equality. What Clausius equality says is dq by t, that is equal to ds. Okay, since I know how much amount of heat is being transferred, so I can find out what is the change in the entropy if it was a reversible process. But since this is not a reversible process, so let's see how we will tackle this problem. Okay, so first you focus your attention only on the surrounding. Okay, so this surrounding, it is maintained at a temperature which is constant, that is 300 Kelvin. Okay, so basically it is acting as a thermal reservoir. So it is accepting heat, but the temperature is not changing. That is what the thermal reservoirs do. They take in heat or they supply heat without undergoing a change in their temperature, right? So this is a kind of your thermal reservoir. Okay, so what it is doing is it is just taking in heat from the system. Okay, if I write down my first law for the surrounding only, okay, then how? I can write that delta U, that is the change in the internal energy, that is equal to Q plus W. But since there is no work being done on the reservoir or no work is being done by the reservoir, so this thing is equal to 0. It is only exchanging heat with the system. Okay, so in this case your Q is equal to delta U. Okay, so if I want to estimate the change in my entropy, I can equally write this equation, delta S is equal to Q by T for the reservoir, that is for the environment E. I can write it as Q upon TE. Okay, but Q is now equal to delta U, which is a state function. Okay, so I can still use this equation. So for thermal reservoirs, you can still use this equation whether the process which is taking place, it is reversible or irreversible. Okay, so in that case, what is your Q, or for that matter your delta U, that is equal to 600. So 600 divided by your temperature of the environment, that is 300. So your delta SE is equal to 2. I have mistakenly written joule per mole. So you all know that the change in entropy, that is equal to Q by T. So it should be Joule per Kelvin. So keep this in mind. Okay. So this much we have found. Now they have asked you to estimate what is delta SF. Since we cannot apply our Clausius equality, what we will do is we will write down your mathematical statement for the second law. What does it say? For any process, the total entropy of the universe increases. What does that mean? It means that your delta SE plus delta SF, that should be greater than 0. We have already calculated delta SE, that is equal to 2. So 2 plus delta SF should be greater than 0, or your delta SF should be greater than minus 2. So we have got the values for both delta SE and delta SF. Now see which one is correct. Out of all these 4, D is correct. Okay, so this is the right answer. If you like this video, please don't forget to subscribe to my channel. Also like this video, and thanks for watching.